This video is about a naturally occurring angle deception countermeasure called Glint. It's about what an RF missile seeker in quotation marks sees as it attacks a large distributed target like a surface ship, and specifically about the effect of the target on the missile seeker antenna pattern. I mean, ultimately what we want to be able to do is to build a jammer that causes artificial glint. Now, the seeker antenna is like the eyeball of an RF missile, and it's normally designed to have a kind of a flashlight beam shape. The eyeball shines the flashlight beam on the ship, and that's how it tracks the target, and guidance signals are derived from the antenna pointing direction to make the missile hit, for example, a surface ship. Now, the antenna pattern, the term, refers to the angular shape of the antenna gain pattern. It will have a large main beam and some kind of side lobe structure. Now, the antenna pattern is usually measured by scanning the antenna over a point source emitter. Then the received power is measured and correlated with the antenna scan angle to get the beam shape. But what happens if the antenna is scanned over a ship, which is not a point source target? It's a distributed target. A ship has lots of separate scatterers, all distributed in angle and range, and all of those reflections arrive coherently back at the seeker antenna. So what does that do to the seeker antenna pattern if we just do the same procedure as I mentioned before to measure the pattern? The important thing to understand is that the antennas transmit and receive radiation patterns are the same, and that's because the antenna is just a bunch of metal, plastic, and pipes. And that means that scanning the antenna over a point source target like a decoy is not the same thing as scanning the antenna over a large distributed target like a ship. So what does that radiation pattern look like when the antenna scans over a cluster of reflectors like a ship? And more importantly, at what angles are there stable track points, since that's where the seeker sees the ship? Now, to answer this question, a few years ago I modified two engaged sub-applications to work together to calculate what I'm talking about. Now, what this pair of applications does is easy to visualize, but it's a bit complicated to explain. So, picture a stationary ship on the sea surface, and the ship is encrusted with a bunch of randomly placed reflectors. Now also picture a sea skimmer missile a couple of kilometers away. The missile body is pointing at the ship, and the missile is stationary. It's just hanging some height above the sea surface. Now the body of the ship has some orientation, some random fixed heading relative to the missile. And now the applications sweep the seeker antenna beam over the ship from left to right, let's say, and the RF power, the skin echo, is recorded, and so is the discriminator voltage which drives the seeker antenna, and that's it. Now this exercise produces one radiation pattern and one set of stable track points. Now, unsurprisingly, the results change if the ship orientation changes relative to the seeker, which it will in real life if the missile flies a little bit cross-range, or if the ship is turning, or both. My idea was to see how the antenna pattern and stable track points change as the ship heading is advanced in, for example, hundredths of a degree increments. Now remember, the ship is big compared to an X-band wavelength, so small changes in ship heading can cause big changes in those files. So I made another software modification to automatically repeat the calculation for different ship headings. So here's what the seeker antenna pattern looks like as the ship orientation is changed through 1 degree in 100th degree steps. That's 100 steps per degree. At each step, the angular position of multiple stable track points is shown. Now the most noticeable feature is that the antenna pattern is distorted by the ship, and the side lobe region is especially dramatically affected. I'll keep replaying this loop while I talk so you can see the same 1 degree of ship heading change just repeated. Extending the video beyond this example 1 degree window would be a ferocious amount of work since every frame has to be individually prepared, and going past 100 frames doesn't really teach us anything new. It's interesting to see glint happening. Glint is a property of any large distributed target. Radar designers discovered very quickly when they were trying to track a ship or an aircraft that sometimes the aim point of the tracking radar moves outside the physical bounds of the object. That's glint. Here's a kind of a cartoon animation to illustrate what I mean. These are not measurements. I just want to explain something. Now, when a seeker looks at a distributed target like a ship, it doesn't see what we see with our eyes. Ships kind of twinkle to a seeker. The antenna instantaneous aim point stays mostly on the ship, but it wanders, and it can wander pretty far. It can even wander outside the physical envelope of the target. And here it is happening in the graphs. Occasionally, the sum pattern becomes extremely distorted, and there is no stable track point within the physical bounds of the ship. That's the ship in the middle there. Glint is known to be strongly correlated with signal fades, and we can see that happening in this video too. Notice that the main beam gain is highly distorted and depressed when the track points are outside the physical bounds of the ship. And having looked very closely at the results of this software experiment, I am very sure I know what causes glint, and it is not the textbook explanation. It's something different. But this isn't the place to talk about that. I might talk about that later. Anyway, this concludes a look at what I think is a unique and interesting naturally occurring angle deception effect. It is what happens when an RF seeker tries to angle track a physically large cluster of metal reflectors like a ship.